During a typical pre-flight inspection or fueling operation, careful attention is usually given to such areas of the aircraft as fuel levels, engine oil level, tire and brake condition, control surfaces, even windshield cleanliness. But what about the battery? Because it is not always easily accessible, it is often overlooked during these routine inspections. Consequently, the battery sometimes suffers from just plain neglect. Although not very complex, the battery is a very necessary part of the modern aircraft. Because it is not very complex, the battery is many times overlooked as the source of the problem. Servicing and maintaining aircraft lead-acid and nickel-cadmium batteries is one of the many responsibilities of the modern A&P mechanic. As a result, this presentation is designed to help the A&P understand typical lead-acid and nickel-cadmium batteries which are employed in all types of modern aircraft. Basically, what is an aircraft battery? It is a simple device which changes electrical energy into chemical energy and holds it in this state until needed. Upon demand, this chemical energy is changed back into electrical energy. The battery, under normal operating conditions, does not supply power for the electrical system while in flight. Its main purpose is to supply power for the starting system as well as to act as a stabilizer for the generating system. There are two types of aircraft batteries in common use today: lead-acid and nickel-cadmium. Since the chemistry of energy change between the two is quite different, a good knowledge of both types is important. In part one of this program, we'll discuss the basic lead-acid battery, its construction, chemistry, ratings, dry charged batteries, servicing equipment, testing, charging procedures, installation, and servicing. The lead-acid battery construction. The basic aircraft lead-acid battery consists of these components. 1. The case. 2. The case partitions. 3. The vents. 4. The terminals. 5. The grid and tabs. 6. The positive and negative plates. 7. The plate separators. The grid is an alloy of lead and antimony cast into a framework to hold the active elements of the battery. The negative grid plate has an active element known as spongy porous lead, which is dull gray in color. An expander is mixed in with the spongy lead to prevent it from contracting into a dense form during its chemical cycle. The active element in the grid of the positive plate is a highly porous compound of lead peroxide. This crystalline substance is brown in color. The negative and positive plates are physically separated by a microporous rubber material having vertical ribs next to the positive plate. A loose fiberglass mat is sometimes placed next to the positive plate to retard the loss of lead peroxide during continued chemical cycling. The cell elements of a battery are made up of positive and negative plates and separators. In a single cell group, there is one more negative than positive plate to allow exposure of each side of the more active positive plate to the negative plates. The ampere-hour capacity of the battery relates to the area of each cell element which is exposed to the electrolyte. The voltage of each cell is the same regardless of number or size of plates per cell. A high-impact molded case houses these cell elements in compartments that make up the complete battery. In many older style batteries, cell posts stick up through individual cell covers and are sealed to the cell with a tar-like compound. Connector straps connect the cells together. Newer style batteries have a one-piece cover with only the negative and positive terminals protruding. The cells are connected through partitions below the cell cover. Venting and servicing is provided by an opening in each cell. Aircraft batteries are provided with spill-proof vented filler plugs to prevent loss of electrolyte when the battery is subjected to unusual attitudes. Aircraft battery terminals may be located on the top or side of the case, with the polarity molded into the case or cover for easy identification. Side-mounted terminals are often fitted with a quick disconnect connector in which the cables are attached to the battery with slip-on connections. The final component of the lead-acid battery is the electrolyte. Electrolyte is made up of a mixture of about 35% sulfuric acid and 65% water by weight. This mixture produces a specific gravity of about 1.265 at 80 degrees Fahrenheit. Question: what is the active element in the negative plate? The positive plate. The negative plate, spongy lead. The positive plate, lead peroxide. Lead-acid battery chemistry. 4 elements are involved in the chemical action which takes place in the lead-acid battery: oxygen, O2, hydrogen, H2, lead, Pb, and a sulfate radical, SO4. During the discharge phase, electrons flow through a conductor from the lead plate to the lead peroxide plate. As the lead loses some of its electrons, a chemical change takes place. Sulfate radicals, SO4, from the electrolyte, join some of the lead to form lead sulfate, PbSO4. When the sulfuric acid loses its sulfate radical, the remaining hydrogen takes on oxygen from the lead peroxide. Water, H2O, forms in the electrolyte, and the lead peroxide becomes lead, Pb. Sulfate radicals from the acid now unite with the lead on the positive plate and form lead sulfate. When the active elements of both plates become lead sulfate and the electrolyte is diluted, there is no more chemical energy to change to electrical energy. To charge a battery, a source of direct current is attached to the battery with the positive terminal to the positive plate and the negative terminal to the negative plate. Electrons are forced through the negative terminal of the battery to drive the sulfate radicals from both the negative and positive plates back into the electrolyte. As the sulfate radicals are driven from the negative plate, the lead sulfate becomes lead. As the sulfate radicals are driven from the positive plate, oxygen from the water unites with the lead on the positive plate to form lead peroxide. When this chemical change is complete, the battery is fully charged. If the charging voltage remains constant, electrolysis will take place. During electrolysis, water is broken down into its component elements of hydrogen and oxygen. Hydrogen is liberated as a free gas at the negative plates and oxygen as a free gas at the positive plates. The gases formed on the plates tend to insulate them and increase the internal resistance of the battery. Even though the charging voltage is held constant, the gas formation causes the charging current to decrease. If a battery is allowed to sit for a period of time in a discharged condition, or if the electrolyte level is low for a period of time, the lead sulfate will harden. A battery in this condition is said to be sulfated. It may be possible to remove the hardened sulfate by a constant current charge until there is no rise in specific gravity for a 2-hour period, then charge at 10% of the normal rate for 60 hours. If the battery is not restored to a full charge condition, it should be discarded. The electrolyte changes its density, or the amount of acid relative to water. As the battery discharges, the amount of water in the acid increases, decreasing the electrolyte density. A hydrometer is used to measure the density or specific gravity of electrolyte, thus indicating the condition of charge of the battery. The specific gravity of electrolyte for a fully charged battery is normally 1.275 at 80 degrees Fahrenheit. Chemically, when a battery is fully discharged, the specific gravity of the electrolyte is about 1.150. Since temperature affects the density of a liquid, a temperature correction must be applied to the specific gravity of the electrolyte. As you see, the density varies 0.004 of a point for every 10 degrees Fahrenheit. For example, an electrolyte having a specific gravity of 1.240 at 100 degrees Fahrenheit would have a corrected specific gravity of 1.248. Electrolyte for a new battery may be prepared by mixing battery quality concentrated sulfuric acid with pure water. Mix 1 part of acid by volume with 3 parts of pure water. Warning: when mixing electrolyte, use eye protection as well as acid-proof gloves and apron. Use only clean glass, plastic, or earthenware containers for the acid. When mixing electrolyte, slowly pour acid into the water, stirring constantly. When acid and water are mixed, considerable heat is generated. Warning: never pour water into acid. The water will boil and splatter acid out of the container. Neutralize spilled acid with bicarbonate of soda, baking soda, and water. Question: what forms on the plates of a discharged battery? Lead sulfate. Battery ratings. The voltage of a lead-acid battery is determined by the number of cells. Each cell having a corrected specific gravity of about 1.265 will have an open circuit voltage of about 2.10 volts. The capacity of a lead-acid battery is expressed in ampere hours. 1 ampere hour is the flow of current of 1 ampere or 1 hour. The rate at which the current flows from the battery determines the amount which can be drawn. To be meaningful, a specific discharge rate must be indicated. The standard rating for aircraft batteries is the 5-hour discharge rate. The 5-hour rating is the ampere-hour capacity of the battery at a current flow which would cause the battery voltage to drop to 1.75 volts per cell at the end of 5 hours. To indicate the capacity of the battery for engine cranking, 2 other ratings are sometimes given: a 20-minute rating and a 5-minute rating. Question: what is the open circuit voltage of a fully charged lead-acid cell? 2.10 volts. Dry charged batteries. To make battery storage and shipping less difficult, batteries are manufactured to a dry charged state. The plates are fully charged or formed, then dried, and the battery is assembled and sealed to prevent entry of moisture. To activate a dry charged battery, the seals are removed from each cell and electrolyte poured in. The battery can be placed in service immediately, although for best results, a boost charge and a check of electrolyte level after 1 hour is recommended. Question: when mixing battery electrolyte, do you pour water into the acid or acid into the water? The acid is always poured into the water. Lead-acid battery servicing equipment. The lead-acid battery servicing equipment consists of a servicing kit containing a hydrometer, syringe, non-metallic brush, bicarbonate of soda, pure water, and a battery cell condition tester. This kit should be marked lead-acid. 2 types of battery chargers are commonly used on aircraft lead-acid batteries: the constant current type and the constant voltage type. Safety apparel should include a face shield, acid-proof gloves, and apron. A complete first aid kit should be in an easily accessible area. Question: what is meant by pure water? It is water that is clear, colorless, odorless, or distilled. Battery testing. The specific gravity of the electrolyte is a measure of the general condition of a battery's charge. Using a battery cell condition tester on each cell will indicate the condition of individual cells. Note, with newer style batteries having internal cell connectors, individual cell voltage cannot be measured. So, check the electrolyte level of each cell and add pure water as required. If the battery is on the service bench, apply a load of about 150 amperes for 3 seconds. If the battery is in the airplane, crank the engine for 3 seconds, then apply a load of about 10 amperes or turn on a taxi light for 1 minute. Measure the voltage across each cell with a low-range voltmeter. The battery is in good condition and fully charged if the voltage of each cell is 1.95 volts, and all cells are within 0.05 of a volt of each other. The battery should be charged if cell voltage on any of the cells is below 1.95 volts. If there is a difference of more than 0.05 of a volt between any of the cells, a cell is defective and the battery should be replaced. Question: what is the best method for measuring the condition of charge of a battery? The hydrometer test for specific gravity. Charging procedures. Constant current charging. In order to charge a battery, the source voltage must be higher than the battery voltage. As the battery charge continues, the battery voltage increases, making it necessary to increase the charging source voltage. It is this voltage variation which makes it necessary to monitor the charging operation to keep the current constant at a desired rate. The battery manufacturer specifies the charging rate based on the plate area per cell. A rule of thumb for constant current charging is to charge at no more than 7% of the ampere-hour rating of the battery. For example, a 35 ampere-hour battery should be charged at a rate of no more than 2.45 amperes. The temperature of a battery should not be allowed to exceed 125 degrees Fahrenheit during charging. As long as the outside of the battery is not excessively warm to touch, this condition has probably not been reached. The effective temperature on the charging rate of a battery is considerable. At 80 degrees Fahrenheit, a half-charged battery will accept 25 amperes from a 14.4 volt source, while at 0 degrees Fahrenheit, it will accept only 2 amperes. A battery is considered to be fully charged when 3 consecutive hydrometer readings, taken an hour apart, show no change in specific gravity and all of the cells are gassing freely. Question: what would be a safe current to use on a constant current charge of a 40 ampere-hour battery? 2.8 to 3 amps. Constant voltage charging. The generator system in an aircraft provides a constant voltage charge to the battery by regulating voltage output slightly higher than battery voltage. When the engine is started, the battery is in a partially discharged state represented by point A. Point B represents the maximum regulated charging rate. The maximum current flows until the battery voltage reaches that limited by the voltage regulator at point C. The charging current drops until the battery is fully charged, as indicated by point D. When the engine is shut down, the battery voltage will drop to normal open circuit voltage shown at point E. A fast charge cannot return a battery to a fully charged condition, so it is often used only to charge the battery enough for it to start the engine. Then the aircraft generator will complete the charge. Caution: when a battery is being charged, a highly explosive mixture of oxygen and hydrogen gas is emitted, so use extreme caution with open flame or when working on electrical connections near a battery. Question: what is a constant voltage charge often used for? To charge the battery sufficiently to start the engine. Battery installation and servicing. FAA and manufacturer-approved practices must be followed for battery care and servicing. The battery must be mounted securely. Caution: do not put too much pressure on the battery container or on the battery, as damage to the battery may occur. Battery cables and terminals should be inspected for cleanliness and tightness. Replacement batteries must be FAA-approved type. Battery location must be in an approved area. Batteries must be vented to the outside of the aircraft. In some aircraft installations, fumes are directed through a sump jar containing a bicarbonate of soda solution. Here, the fumes are neutralized before they exit the aircraft. Corrosion should be neutralized and the area painted with acid-resistant paint. The electrolyte level should be regularly checked and adjusted with colorless, odorless water, distilled water if possible. Do not overfill. Electrolyte should not be added for normal battery servicing. Do not add water if the battery will be subject to freezing temperatures before use, as water will not mix properly with electrolyte and freezing damage may occur. Warning: when working around aircraft batteries, rings, metal watch bands, and neck chains should be removed, as they may inadvertently short across the battery potential and cause a severe burn. Question: what solution is used to neutralize lead-acid battery electrolyte? Bicarbonate of soda and water. Up to this point, we've discussed the lead-acid type battery. The importance of frequent inspections and periodic preventive maintenance cannot be overemphasized. Manufacturers have proven that the most common cause of battery failure is low electrolyte level, and this problem is most often due to neglect. In Part 2 of this program, we will study the nickel-cadmium aircraft battery. Nickel-cadmium batteries, commonly called NiCad batteries, have come into popular use in the past few years because of their ability to accept high charge rates. They also have the ability to accept high discharge rates without the voltage drop associated with lead-acid batteries. In Part 2 of this program, we will discuss nickel-cadmium battery construction, chemistry, thermal problems, servicing equipment, servicing, testing and charging, and deep cycling. Nickel-cadmium construction. The base of the NiCad battery is its plate material or plaque. Powdered nickel is fused or sintered to a fine mesh nickel screen to form an extremely porous material. The positive plate plaque is impregnated with nickel hydroxide. The negative plate plaque is impregnated with cadmium hydroxide. Nickel tabs are welded to the corner of each plate, and the plates are grouped into core assemblies. The positive and negative plates are sandwiched in a multi-layer between special separators of fabric and plastic. This stack-up is bound with a plastic binder to form a compact assembly. A cover and vent assembly is attached to the plate stack-up to provide a foundation for the cell, and the filler cap allows for servicing and venting. A polystyrene or nylon case houses the cell. 9 or 10 individual cell assemblies make up a 12-volt battery, while 19 or 20 cell assemblies make up a 24-volt battery. NiCad batteries are usually fitted with a quick disconnect connector in which the cables are attached to the battery with slip-on connections. The electrolyte is made up of 30% potassium hydroxide and 70% pure water by weight. The specific gravity of this solution is about 1.24 to 1.30 at 80 degrees Fahrenheit. The specific gravity of the electrolyte does not change with the condition of battery charge, as the electrolyte serves only as a conductor and does not undergo a chemical change. Potassium hydroxide is a strong alkali or base and should be handled with as much caution as an acid. Question: what is the active material on the positive plate, the negative plate? On the positive plate, nickel hydroxide. On the negative plate, cadmium hydroxide. NiCad battery chemistry. During the charging phase, oxygen is driven from the cadmium hydroxide of the negative plate, leaving metallic cadmium. The nickel hydroxide of the positive plate accepts the oxygen and becomes more highly oxidized. Gassing of the cells occurs near the end of charge, when the water in the electrolyte is decomposed by electrolysis. When the battery is fully charged, electrolyte is driven from the plates and will be at the highest level in the cell. One of the characteristics of a NiCad battery is that its constant voltage is held to a point approaching complete discharge. Another is the fact the electrolyte does not enter the chemical cycle. Because of this, there is no simple way to determine the condition of charge, as the specific gravity remains the same in the discharged condition as in the charged condition. The only way to know exactly how much charge the battery has is by the ampere hours of charge put into it. Question: how is the condition of charge of a nickel-cadmium battery determined? By the number of ampere hours of charge that has been put in. Thermal problems. The low internal resistance and voltage delivery characteristics of a nickel-cadmium battery vary as an inverse function of temperature. This means that an increase in temperature will cause a decrease in voltage and internal resistance. During prolonged engine cranking, the center cells become extremely warm. These warmer cells have lower voltage and lower internal resistance than the other cells of the battery, causing an imbalance within the battery. The severity of this condition is directly related to the length of starting time. When the engine does start and the generator comes online, a high current is immediately put back into the battery, which aggravates this condition further. If some of the cells are unbalanced because of large temperature differences, the high current output of the generator will continue to cause still more heat. This further lowers resistance of the affected cells. This condition is known as thermal runaway and can become critical to the point of destroying the battery. To help prevent thermal runaway, sensing devices which monitor either temperature, current, or voltage may be installed. These devices warn the pilot of an impending problem, so he may take proper action to prevent thermal runaway. Question: what causes thermal runaway? Unbalanced voltage and resistance of the cells causing excessive current flow and heating. Servicing equipment. Servicing the NiCad battery requires special attention and special equipment. Most important, it requires separate facilities and tools from that of lead-acid battery servicing. The alkaline electrolyte of the NiCad battery is chemically opposite to the acid electrolyte of the lead-acid battery, and considerable damage could result from acid contamination of a NiCad battery. A servicing kit containing a hydrometer, syringe, non-metallic brush, boric acid solution, and distilled water should be marked for nickel cadmium. Safety apparel should include face shield, caustic-proof gloves, and apron. A first aid kit should be in an easily accessible area. Charging equipment may be of the constant voltage or the constant current type. A built-in timer controls the charge and discharge cycles. Load banks control the discharge rate. Some charging units have built-in shorting circuits for shorting individual cells or for simulating starter load on the battery. Question: why should nickel-cadmium batteries have their own area for servicing? Because the fumes from lead-acid batteries will damage nickel-cadmium batteries. Battery servicing. The NiCad battery should be carefully monitored by the A&P at least every 50 operating hours, more frequently if any troubles have been reported. The battery container should be free of any contamination, and the vent system should be clear and operating. A white powder, potassium carbonate, forms on the top of the cells when the electrolyte spews out and combines with carbon dioxide. This is an indication that those cells could have charging problems and are in need of servicing. Adjustment of electrolyte levels should be done only in the shop where the condition of charge of the battery may be determined. A typical shop service sequence consists of scrubbing the battery with a non-metallic brush and boric acid solution, then rinsing with tap water and air drying. Check for current leakage between the cells and the case. More than 100 milliamperes is excessive, and the battery should be disassembled and cleaned. Question: what is used to neutralize the nickel-cadmium battery electrolyte? Boric acid solution. Testing and charging. Using a constant current charger or a charger analyzer, charge the battery at its 5-hour rate until it reaches its recommended voltage. For a typical 19-cell battery, this would be 30 volts, or 1.58 volts per cell. If a constant voltage charger is used, it must be adjusted to the value recommended by the manufacturer. A battery is considered to be fully charged by a constant voltage charger when the charging current tapers off and stabilizes. When the battery is fully charged, its electrolyte will be at the highest level in the cells. Adjust the level as required, using only distilled water. To accurately determine the true state of charge of a NiCad battery, a measure of its ampere-hour capacity must be taken. Connect the battery across a load bank and discharge it at its 1 or 2 hour rate until an average of 1.0 volts per cell is reached. Note the time. If this discharge time is less than 70% of the time specified by the manufacturer, there is indication that the capacity of the battery has been decreased and a further discharge or equalization is required. Question: what should be the cell voltage of a fully charged nickel-cadmium battery? 1.58 volts per cell. The deep cycling procedure. A battery can lose some of its capacity if one or more of the cells is out of balance with the others. To remedy this situation, the battery must be deep cycled. During deep cycling, the battery is completely discharged, allowed to remain in this condition for the period of time specified by the manufacturer, then charged back to 140% of its ampere-hour capacity using a constant current charge. Discharge the battery at a lower rate than before until the individual cell voltage is about 0.2 of a volt. With the battery load still applied, Individually short each cell with a shorting strap. Allow the battery to sit for 3 to 8 hours in this condition to allow all the cells to become completely discharged. Remove the shorting straps and place the battery on a constant current charge at its 5-hour rate for 7 hours. This will put 140% of the rated ampere-hour capacity into the battery. In the last 5 minutes of charge, measure the voltage of each cell. Any cell not having between 1.55 volts and 1.80 volts at a temperature of 70 to 80 degrees Fahrenheit is considered faulty and must be replaced. Question: what is meant by deep cycling? The battery is completely discharged, all the cells shorted, and allowed to rest, then recharged to 140% of its rated capacity. Before the battery is returned to service, a final check is made of the torque on all the intercell connections, the level of the electrolyte and the leakage current, and the service performed is entered into the aircraft battery log. This log provides a record for the A&P to spot future problems. Servicing and maintaining aircraft batteries is not complex. The key to consistent and prolonged battery service is routine preventive maintenance. Remember, the start of any successful flight must begin with the battery. Clear prop. It is your knowledge, experience, and the responsibility you assume that convinces others you are a professional in the highly technical field of aircraft maintenance.